Shall we start now? Hello, Vishnu sir.
Yes, ma'am.
Good evening, all. I am happy to say that we have completed 2/3 of our workshop. All of you to this 11th session of our program, and over to Professor Vishnu.
Thank you very much, ma'am. And yeah, we are going to continue with the discussion that we had in the last session. So, last session, day before yesterday, we were trying to see some techniques for interpolating some functions. Interpolating in the sense that suppose that we are given some x values as well as corresponding y values, whereas the function is not known to us. The function f is known to us, but some values are given to us, most probably created or generated using some experiment, got using some other technique. So the function is actually not known to us. In that situation, we have a pair of values, xy pair of values. So what we essentially do is, if we want to compute one y value corresponding to one particular x value in between the given set of x points, we use the technique called interpolation. Okay, so that's essentially the idea of interpolation is. So the idea is, suppose that we are given some x values and corresponding some y values are also given. Essentially, what we mean is that some points on the plane is given to us. If some points on the plane is given to us, we are trying to find a curve in such a way that the curve passes through the given point so that we can predict. We are actually trying to construct a curve in such a way that the curve passes through the given points so that we can predict that corresponding to one particular x value for which y value is not known, we will use this particular curve to locate the corresponding y value. That's what essentially we are doing. It's a kind of approximation using the given set of data points. If the x value for which we need to find y value is in between the given x values, we call it to be interpolation, and if it's outside, we call that to be extrapolation. So what I understand is that extrapolation is not that accurate compared to interpolation. And one more thing is that if you have too many data points, having too many data points is also not a good thing, because what happens is that the curve becomes too much oscillating. Okay, the curve becomes too much oscillating. The curve tries to become, if you are constructing a polynomial, the curve tries to become a polynomial with a huge number of times, a large degree. So in such a situation, we may be expecting that the curve to be somewhat more accurate. But what I understand from the theory, I don't exactly know the complete theory behind that thing. What I have read is that maybe some of you might have already gone through a course in numerical analysis, and maybe even experts in numerical analysis. I am not, of course. What I'm trying to do is that, provided we know the technique in numerical analysis, I'm just trying to explain how to use Python programming for implementing that technique. I'm not at all trying to explain or not at all trying to convince you about the complete theory behind numerical analysis, because I don't know numerical analysis, to be frank. I'm just using it for solving problems. I don't know the analysis. The analysis part is not very much known to me. Only the numerical part is known to me. Okay, numerical part only I'm trying to explain to you. So assuming that the technique, whatever technique I'm reading from textbooks are correct, I'm not questioning the authenticity, the correctness of those techniques. You also may be knowing the technique, and you may be probably knowing better than me that why this technique is correct and why it's giving the correct answer most of the times. Okay, I'm assuming it to be granted. So as I told, the interpolation is something like that, and extrapolation is that we are trying to find the y value corresponding to some x value which is outside the set of world. Outside in the sense that, suppose that we are given values from x0 to xn or x1 to xn. So outside means that if you are arranging this x1, x2, etc., xn in the increasing order, outside in the sense that it's before x1 and after xn. It is outside the interval x1 to xn. That's what we mean by extrapolating with the value outside. Okay, extrapolation seems to be somewhat not much supported by this numerical analysis for various reasons, but interpolation is. And one more thing is that in Lagrange interpolation and Newton forward difference as well as backward difference interpolation that we have seen in the last session, we have seen that when we have too many terms in the interpolating polynomial, the computation slows down very much. Okay, the computation is really slow. because most of the times, of course, we are using some ordinary PC for all these computations. Provided we are using a supercomputer, the computation can become a bit more faster. But I'm not very sure about that. If it's because of what I call the lower capacity of my machine, or not lower processing capacity of my machine is not, it's getting slower. But anyway, what I understand is that if you are having a large number of data points, you cannot expect the interpolation to be too fast. You cannot expect the interpolation to be too accurate also. Okay. So we were using our own method for computing the interpolation, our own method for computing the interpolation polynomial, as well as interpolating the values. In the last session itself, we have seen there is a built-in method available in what the model that we were using was numerical Python, numpy. There is a built-in method available in numpy which will actually help us to interpolate. We will start with that built-in method, and after that, today we will move to another method which is available in a module called sympy. Sympy means scientific Python. It's you can say that there are intersections between sympy and numerical Python, of course. But sympy, we will try to see some methods available for numerical analysis, especially for interpolation. And after that, in today's session, we will try to see something called curve fitting. Okay, curve fitting using least square method. There are several other methods also, but least square method is one thing that we are going to focus on. I will be trying to show you the computation using some standard textbook in which this least square method is actually explained, so that you also can see and understand what exactly I am trying to do, what exactly I am trying to achieve. So we are going to start a program initially with using the interpolating functions available in numerical Python itself. After that, we will move towards constructing a program using the least square method. Okay, let me start sharing my screen. My spider window is here. Okay, first of all, we are trying to use the interpolation polynomial already available, interpolating function already available in numerical Python. So even though we have discussed about thing in the last class, last session, I will just try to explain it once again so that we can just immediately refresh what exactly we have done. So as in the previous sessions, we will be trying to plot also whatever data that we are having so that we can get a better understanding about how the interpolation as well as how the set of values are, how the interpolation as well as how the actual function is moving. Okay. So let me import numerical Python first of all. The standard command we have been using in the previous sessions. Import numerical Python mpy as np, a shortcut. Now for plotting also, pyplot as plt. These two are some standard short names used at many places. So now let us create something x square. Suppose that we plot y is equal to x square. So x is equal to, suppose that we are choosing from np linear space. Let us choose linear space, say between 0 and 2, some 20 points. Y correspondingly, let us just square, or maybe even we can cube x square. Remember that squaring of a number of items simultaneously is possible because we are using the numerical Python generated array. Okay, doing such a thing using a list is not possible. What I'm saying is, suppose that we are defining x to be equal to list 1, 2, 3, just for example, and suppose that we write y to be equal to x square. This will not work because x is a list. This is a Python object, standard Python object. So a standard Python object list cannot be squared just like that, but you need to do it individually. If you want to achieve this, this is wrong. So if you want to achieve this, what you should do is, if it's an ordinary Python list, what you should do is take don't take x square because x you should not use here. Instead of that, say a square for a in x. This is correct. This is wrong. Okay. I hope that you can understand this. So this is quite correct. This is okay because numerical Python array can be squared. There is no problem. It's permitted. So y is equal to x squared. So we have generated y values and x values are already there. Now, if you want to plot, we can see that this the plot is actually that of a parabola. PLT plot x y and PLT show. Okay, need to save it. Saved, running. So you can say that this is very close to this. Okay, in the screen, I don't know whether it's completely visible. Okay, let me just reduce the number of points further. Now you can see that this is not a smooth curve. Oh, I'm really sorry. I did not actually observe that I'm muted. Sorry. So I'll just explain these things once again. So we are importing numerical Python first of all. Numerical Python is imported. Matplotlib pyplot is also imported. After that, a number of points, x points are created using the linear space command available in numerical Python. Only 5 points are created between 0 and 2, and we are trying to see how the curve looks like. So if you are trying to plot the x and y coordinates, we are now seeing that it's not a smooth curve, okay, because number of points is very less. If you use lesser points, you will be again getting the curve to be a bit more non-smooth. If you use more points, you will be getting the curve to be smooth. Okay. So these are the points that we have. Now, what we are going to do is, okay, let me just suppress this. Later we can see these things. Okay, this commands also I will move. I wanted to just say that with ordinary list, we cannot apply this squaring command. Okay, that's one thing that I wanted to clarify. If you define x to be just a Python list, say 1, 2, 3, you cannot apply. If you define x to be this, you cannot apply y is equal to x squared. You cannot write y is equal to x squared. That will create an error because ordinary list cannot be straight away squared. Instead of that, you need to use list comprehension like y is equal to a square for a in x. Don't use x square for x in x. Okay, that will again make a lot of confusion that may not work. That's one thing that I want to clarify. Okay, suppress. So it's plotted. Now we are going to make use of the interpolation command available in directly available in Python. So the interpolation command available in Python is interp in numerical Python. Okay, so the thing is that interp actually gives you only one. Okay, so only the newly interpolated value this interp gives. Okay, for example, suppose that we want to interpolate 4. Suppose we need to find. It is not giving any curve or anything like that. Suppose we need to find the value of y at x equal. So which point we have taken 0 to 10. What are the points that we should know? So what are the points we have taken? Print x. So we are getting 0, 0.22. Okay, so safely we can use 0.5. X at 0.5. So if you want to find y value corresponding to x value equal to 2.5, what you need to simply do is use the np dot inter x value for the y values and for the x corresponding to the x values and y values given. That's it. So Okay, let us try to plot a point also corresponding to that. After that, print y value. Let us see. The number is coming out to be equal to 4.0. It's not correct. 4.0. Okay, let us plot that point also once. PLT plot x value, y value. I don't know whether we can do it like that because maybe we require some arrays to be provided. Let us see if it works. And in red circle, I don't know, circle or dot. Okay, let's see the plot now. Oh, the curve seems to be too old. We have taken 2.5. It's outside the range. Okay, let me just take not 2 point. Which value we were saying about? 0.5 we were saying about. Sorry, that's a mistake. Okay, what's the value corresponding to that? 0.5 corresponding to that. The result given is 0.25. Okay, that seems to be somewhat reasonable. What is the command for increasing that marker size? Marker size 20. Okay, can see it. So this is how we can interpolate for one particular value. You don't have to write down the polynomial. You need not do anything. But internally, Python, numerical Python may be doing all these things. Okay. So let me just update the entire thing in the Google Sheet, that the link to which I have given. Okay. So the Google document link is here. You can find the entire code here. And one more thing to remember here, one more thing to note here is that the interp function available in numerical Python does not assume that you are using what you call equally spaced points. Such an assumption is not there. Okay, such an assumption is not there. For example, we can try to change one of the values here. So we see that the x values are given to be 0, 0.22, 0.44, etc. Suppose that we change, let's try to change x value, x1 value. Suppose we change it to 0.2 so that it's not linear anymore. 0.2. But even after that, the value is given to be more or less the same. So interp does not require the data points. Data points means x points. Need not be equally spaced. But remember that in the previous example, Newton forward difference and backward difference, the values are required to be equally spaced. Otherwise, you need to use a divided difference. Divided difference we have not discussed, but the only difference is that instead of using the differences, you need to divide the difference with you need to divide the forward difference or backward difference, whatever you are using. You need to divide that difference with the difference in the data points. For example, if you are using delta square yi, then you need to divide it with xi minus xi minus 1 or xi plus 1 minus xi. I don't exactly remember what it is. You need to divide. Okay, that's the only thing. An extra division is there to make it uniform. But here you don't have to do any of these things. Maybe that interp is doing all these things in the background. We don't exactly know. Okay, that's it about direct interpolation. Now we are going to see interpolate. Okay. Now we are going to see another method provided by another function. Okay, another method provided by another function in Python for interpolation. That function is it's not coming up from a numerical Python, but instead of that, it's coming from a module called SciPython. Module called SciPython. So if we want to use module called SciPython, we need to import that particular function from SciPython. In the same program, we let us try to see that how exactly the result looks like. Are they different? Okay, for using SciPy provided interpolation, we import it from SciPy, import the function we need to, not exactly a function, it's a class of functions, import interpolate. Already we have x and y values, no need to again do all these things. But now, one major change, okay, I'll try to show that major change. See that previously in the numerical Python provided interpolation, we were only getting one value, okay, corresponding to the x value between the data points. We were getting y value. We were not getting it as a function. We cannot use it as a function anymore. It's just a numeric value. But in the case of SciPython provided interpolate, what happens is that a function itself is being provided, like f is equal to or int inter function. We are getting it as function is equal to interpolate, which is the module that we have imported, just like matplotlib dot pyplot imported as plt, and after that we are using dot plt. Just like that, we need to use interpolate dot. The function is interp 1d. Okay, 1d, one dimension. What to interpolate? X points are already there with us. Already we have the x points, y points. If you try to print, I don't think that. Okay, let us try to see. We printed. No, it will not print exactly like that. It will just show that it's a SciPython provided interpolate interp p1d object. It's in our common natural language. Maybe we can call it as a function. Okay, now trying to see the value of y at x is, let's try to see that our x is again x value, y is f of x. See that the previous result was 2592 etc., and result now is, oh, it is not defined, sorry, 0.2529, 0. What is the reference? 9393. Okay, they're exactly the same. The results are exactly the same. But here we are getting, once you interpolate, you have this function available with you. You can use it for anything. We can use it for even plotting. Okay, suppose that we suppose that we plot that also. f of uh, the entire x values. And that's not going to make much sense. I don't know. Okay, let's try to see. Trying to plot that once again. Suppressing plot here. Trying to plot x and y, x and interpolated value using sympy interpolation. Plotting. This is what x and y are plotted, and okay, you can see that. Okay, the 2 points are not equally spaced. Okay, 0.25. Okay, let us try to see using the straight lines itself and see. There is not much difference. Not much difference is there. Okay, more or less looks the same. But if you use fewer points, let us see what happens. Okay, then also there is not much difference. The most important thing that we should remember is that SciPy provided interpolation is a function, whereas numerical Python provided interpolation is just a number. And one more thing is that numerical Python provided interpolation can handle only one-dimensional arrays, whereas SciPython can even handle complex data. Complex number data also can be handled. Two-dimensional arrays can be handled. Complex number is essentially two-dimensional because we need A and B, both coordinates are required. So SciPython interpolation can handle complex data also. Okay, let me update this part also. Okay, otherwise I will update the entire program in the Google Sheet. Sorted. Please check. So there are two types of interpolation actually. One is called linear interpolation, and another is cubic spline interpolation. So in certain situations, cubic spline interpolation seems to be better, and in certain other situations, the linear interpolation seems to be better. So whenever you have the data is well behaved, linear interpolation is just fine. But it seems that whenever the data is not so, it's not very. You don't expect the function to behave nicely. Okay. So in such a situation, you should probably use cubic spline interpolation. But in SciPython and in numerical Python, we have not been in numerical Python provide interpolations. We have not been actually specifying what type of interpolation we should use. Okay, there is actually a way to suggest that which type of interpolation to actually use in our interpolation. By default, linear interpolation will be taken used, but if you want to specify some other interpolation, we can even do that. We'll try to see one example. So let us try to see that what kind of difference is there between linear and cubic spline interpolations, and we will not be constructing any Lagrange polynomial or Newton divided difference Newton polynomial, but instead of that, we will be depending on the numerical Python and SciPy provided interpolation techniques. So linear versus cubic spline interpolation. That's the program name. Once again, we are trying to import matplotlib, numerical Python, everything. Import numpy as np. Import as plt. Next is from SciPython, we import what is the previous thing from SciPython? What did we import it? What did we import? Interpolate, and after that we used interpld. Okay, same command. Interpolate. Interp1d we have to use after that. Now let us try to interpolate the cosine curve, which we know that it's actually a smooth curve, but it's not a polynomial function. But previously we had a polynomial function. We will try to see the difference between the cubic spline as well as linear interpolation. Two techniques available for interpolation. So let us create the data points np linear space 0 to 2 pi. Data points is here. Now y equal to np cos of x. So x and y points are here. Oh, sorry. In linear space, we have not specified how many points. Say 20. Trying to plot plt plot xy. Green. Work. Okay, the plot is okay, but it's not that smooth. If you reduce the number of points further, it's uh, it's becoming worse. Okay. Now let us do two kinds of interpolation. Okay. So f linear. So we are going to create the linear interpolation first. So for that, use interp1d. If you do not specify any type, any extra options are not specified, it's assumed to be linear. X, Y. So F is this is constructed. Now F cubic. So here we need to specify the type of interpolation we require, the kind of interpolation we require, we need to specify. So it's specified using the kind parameter. If you do not specify anything, the kind is assumed to be linear. So linear by default. So we have two. Let us try to plot the curves F linear. We know that this is a cosine curve. Okay, that's clear to us. Maybe we can even create another one so that we can quickly understand that which one is accurate. Okay, let's do that later. Okay, otherwise X is this. Y accurate also will create, or the accurate curve also will try to plot. Accurate curve in the sense that with more points, that's it. The curve is not going to be accurate or anything like that. Let us use more points. Instead of using 10 points, let us use some 50 points. So we will be getting more accurate curve. I didn't mean anything else. NP cos X. I wanted to just plot and see that how far these interpolations give the correct answer. How far different the answers are. I want to just differentiate between these two. So trying to plot F linear and PLT F cubic and this accurate plot, all the plots. Trying to see this also, X accurate, Y accurate also in blue, and Z dots. Okay, what happened? I think if you are using it, you need to just use B here. Oh, sorry, X accurate and Y accurate. That's missing. What's the problem here? Oh, I pasted it here. X accurate is using only 50 points. Okay, the correct curve is there using more points. It's dotted. Okay, now let us try to plot linear and cubic. Try to see linear and cubic. Maybe we can reduce the number of points further to 5. Oh, 5 is really bad. 8. Okay, somewhat better. So now trying to see F linear plotting. X, F linear of X, and black dashes. It's really difficult to see where it is. Let me suppress the accurate plotting to see. Increasing to 15. Okay, not very different. Okay, let us try to increase this range to, okay, let me just try to see. Okay, let's try to see with some other example also, but same time. Trying to see the cubic function also plotted. Let me change the function to something else and change the range also, make it larger. Changing the function also to something slightly different. Okay, trying to plot it using some different x values, new x values. This x is going to be up to 100. Just make it slightly. I'm changing the function. That's it. I'm not doing anything. So this is because okay, we are again using the f linear value and f cubic value on the correct x itself, but instead of that, let us try to use newer x values, x new from the same range, but newer values. Say 30 y new equal to using y linear, okay, using f linear of x new and y cubic using f cubic of x new, plotting x new. Okay, we can straight away use it here instead of providing newer values. Use it here, f cubic here. Trying to see, we have used more points. See that? Which is the green one, which is the black one, and where these are. So what are the results finally? Let us try to see once again. Here we have used, let's see, just use lesser values. So having we plotted this, x and y we have already plotted. That's in green. But what's happening to this value? The black one. Okay. One is red star. Let's try to give some legend also to see. Okay, here because the size of this plot is really small, I'm trying to see how to increase that. How to increase the size of the plotting window. Okay, even if I increase the size, it's not getting increased somehow. So to which function, which one? Green one is was what? Green one was. There is no green one. So automatically the color is chosen. Okay, let us try to see the legend also because otherwise we are not able to understand what exactly it is. So let us show the legend also. PLT legend. One is the X points or the actual data that we have used. The second one is the linear plotting, and the third one is cubic. So actual data is here. Linear is in orange color, and cubic is in the green color. And if you try to plot uh, the actual value also, let us try to plot even that. Okay, let us try to plot this function. Oh, there was a difference that division with 9. Okay, division with 10.0. Let us take it to be 8. Okay, now let me just try to plot inaccurate functions. £20 or 30 points. Once again, y accurate is using x accurate, same function. Now let me try to plot that also. So x and y, x here, y here using dot alone, and therefore the third one is actual function. Trying to see it, but not dot, maybe a curve. The actual function is appearing in somewhat red color. Okay. The actual function is appearing in somewhat in red color, and we can say that the orange colored thing, which is the linear interpolation, is not that accurate, whereas the green colored one seems to be comparatively more accurate. Okay, the green colored one seems to be comparatively more accurate. Therefore, cubic spline interpolation seems to be comparatively better when you expect your data to be not that level, not that smoothly behaving. If you expect the curve to be not that smooth, then interpolation using cubic spline method seems to be somewhat better. Okay, that's probably one guess we can make from this data. Okay, let me just update the Google Sheet with this. Interpolating, which interpolating? I don't understand what you mean by which interpolating. Do you mean cubic or spline? If you're asking about cubic or spline, what happens is that if no interpolation is specified, the linear interpolation is being cubic spline or linear. Sorry, not cubic or spline, cubic spline or linear. If you are not specifying any interpolating method, automatically by default, linear will be used. Linear is much faster comparatively. Okay, when you are using linear interpolation, what happens is that even if you are using the scipy function, scipy straight away calls numerical Python. Okay, it's not that SciPython is doing everything in its own, but when you call for linear, when you call for not just linear, when you call for interpolation using one-dimensional data, SciPython actually uses numerical Python. Even though we are using SciPython calls numerical Python in 10. Okay, let me update with the Google Sheet with all these. Update. The entire sheet is updated. Okay, so the next thing that we are trying to do is, as we already told, the curve fitting. So curve fitting essentially means that so there are different types of curves. Suppose that we have some data given. Okay, x data is given to us, y data is given to us, which essentially represents a set of points on the plane. Suppose that it's given to us. Sometimes we will want to construct a straight line which is very close to that particular data. Very close to that data in the sense that definitely a straight line cannot pass through. If more than 2 points are given, a straight line uh, not probably is going to pass through more than 2 points that's available with us, because these 3 points may not be lying on the same line. So, but instead of that, we will try to plot a line in such a way that that is very close to all these data points. Very close to, in the sense that a distance from that line to the data points. Okay, distance from the line that we are constructing using the least square method to the data points. The sum of squares of the distances, because the distance can be negative as well as positive depending upon on which side of the line the points are lying. So take the line to the point distance. Number of points given will be finite. Once you take the distance between the line and the corresponding points, square them, and take the difference, square them, sum them. So we are going to construct a line in such a way that this sum of squares of the differences in the actual data and the line data, they are very small. The difference is very small. So that's what essentially is the least square method is. Least square curve fitting is essentially that. And why we are calling it to be least square curve fitting is that sometimes we may want to construct a straight line which passes through the middle of the data or very close to the data as much as possible. Sometimes we may want to construct a quadratic polynomial or a parabola, for example. A quadratic polynomial, a parabola, actually, a quadratic polynomial actually represents. We can say that okay, that doesn't exactly mean to be a parabola. It can represent a parabola. So in such a situation, we will be fitting a curve. Okay, we will be fitting the given curve. We will be fitting the given data to a curve. We may fit the given data to a straight line. We may try to fit the given data to a curve, and that in such a way that the difference between the actual data to the points on the curve, square them and sum them. That sum is the least. That's what the least square method is. Okay. So let me just try to show the least square method. I think I will try to share a page from a textbook so that you can easily understand what exactly we mean. Let me just start a PDF page. I'm stopping this first of all. I hope that you are able to see this. This is actually a chapter on curve fitting taken from one book by one Kumar Molugram and G. Shankar Rao. That's actually a book titled, you can see, that's Statistical Techniques in what is it exactly? Statistical Techniques in Transportation Engineering. Okay, this is actually the book name. It's a Science Direct provided book. I can actually buy that book from Amazon, or you can try to see if some soft copies available somewhere. So essentially, the technique is something like this. So we are going to construct in the first problem. We are trying to construct a least square line so that Suppose that we are given a set of data x1, y1, x2, y2, etc. up to xn, yn. So the best fitting curve y is equal to fx, in which in our case y is equal to a plus bx, which is a linear polynomial or a straight line. So it has the least square error. Least square error in the sense that suppose that we are given x values and y values. Okay, we have constructed the value f. The f is there. F is actually a plus bx. So we have to construct line in such a way that we have to find out the coefficients. See, in this particular equation, we need to find is a and b. A and b we need to find in such a way that given yi values and the constructed a plus bx, when we take the difference between y values and a plus bx in xi put into that a plus bx, the difference in these two values, squared it, summed it. After summing it, you are getting some e, which is the error. Okay, least square error. So the least square error, we want that to be minimum. And we know that from the theory of partial differential equations, maxima minima theory, we know that the essential condition for that to be minimum is that with respect to a, the partial derivative should be 0. With respect to b, the partial derivative should be 0. On solving these things, okay, once you solve these things, what you get is you will get a to be this and b to be this. Okay, essentially we are going to make use of this on solving the system of equations or set of equations that we are getting in terms of consisting of a and b. Finally, we will be having a equal to this and b is equal to this. And we know that a is equal to yi sigma xi square. So we need to compute sigma xi square. We need to compute sigma xi into sigma xi yi. All these things we need to compute. And after computing, we can compute a, we can compute b, and once we compute this a and b, we will be getting the final a plus bx, which is passing through the given data with the least error possible. Okay, this is essentially the underlying what do you call method behind using the least square method and fitting the data into a least square line. So here, instead of least curve fitting, we are fitting least square line. Okay, that's what essentially we are doing. So the thing that we have to find out is that we need to compute all these. What are the things that we need to compute? So corresponding to given value of x and y, of course, we can either construct some. We can find out some x and y values, or we can using some other function we can construct some x and y values. X values definitely we have to use NP linear space or arrange for uniformly creating some values. After creating the values, we need to provide some y data also. After doing all these things, we need to compute sigma xi, sigma yi, sigma xi yi. Okay, so xi yi is also required. Sigma xi yi is required. After constructing all these things, we have the formula with us. What is the formula? We have the formula that a is equal to this and b is equal to this. Okay, I hope that this idea is clear to all of you, and I will be making use of this data 5, 10, 15, 20, 25, 16, 19, 23, 26, 30. So we can compare the result with the solution already available here. Okay, so the solution already available here is 0.7x plus 12.3. Let us see that in Python when we are performing the computation, whether it's correct or not. And one more thing is that after that, okay, we can otherwise also we can do something else. We can try to construct a straight line, least square straight line corresponding to the sine curve. Okay, corresponding to sine curve, if you are using the sine curve within the range 0 to pi by 2, that's more or less close to a straight line. If you are constructing sine curve within the range 0 to 2 pi, it's not going to be 0 to pi even. It's not going to be a straight line. You cannot fit it. The data will be completely off. It's full of errors. You should not do that. If you're very sure that your data is not going to fit into a straight line, of course, you should not do that. So this is the essential technique that we are going to make use of. Let us try to see the problem given here first, and after that we will try to do our own problem. So two problems we will try to see for constructing a least square line. Let me stop sharing this screen and going back to Python, going back to Spider. Okay. Now the Spider window is back. going to a new program. I think this I have already updated completely in the Google Sheet. Okay, so new program. So this is the 54th program. 54 least square line dot py. Okay, so let us take the x data to be exactly the same thing that's provided in that textbook. 5, 10, 15, 20, 25. We can straight away use okay, a range itself we can use, because otherwise if you are using range, that's not going to be an array. You cannot square that. Okay, so whenever we are doing something related to numerical Python, do not use range, because if you use range will be providing something very similar to a list. List cannot be so easily used for functions given in numerical Python. So you cannot apply sine directly to that. You cannot apply cos directly to that probably. So instead of that, create an NP arrange array. So in 10 to 20, sorry, not 10 to 20, I think 10 to 5 to 25. 5, 25. Okay, instead of, okay, just one more thing. Okay, let us use linear space instead. It's suggested that use linear space instead of linear space. If you are using 5 to 25, if you, so how much is the difference between these two? 20. So if you divide it into 4, so what are the points that you're going to get? Saving, print x. Oh, sorry. Import numpy as sympy. Sorry, linear space. So value is taken here as 0, 1, 2. So five, 11, 18, 25. So why is it happening like that? 5, 11, 18, 25. Okay, 5 points are required. 5, 10, 15, 20, 25. 5 points. Now, if you include the endpoint is equal to true argument also along with the linear space, what will happen is that even otherwise, I think that will be included, right? Yeah, even otherwise it's getting included. So if you use instead of that, okay, that is not applicable here anyway. Okay, let us, I'll just try to find an explanation for that later. So anyway, we are creating a linear space with these points 5, 10, 15, 20, 25. Now correspondingly, why Okay, why I'm just taking NP array? It must be an object. Maybe keep it inside a list. Same data. 16, 19. I'm copying from that textbook. 16, 19, 23, 26, 30. I'm using this data. So x is there with us. X we have, y we have. So what are the other things that we require? Let us see the formula. In the formula, we require sigma yi, sigma xi square, sigma xi, sigma xi yi. Okay, let us create xi yi or xy. Let's create xy equal to, we need sigma xi y, right? Sigma xi y we can sum anyway. Xy is we can straight away take xy, so there is no problem. We should be able to do that. Okay, maybe otherwise we can straight away also use that. So the formula is that sigma yi, sigma xi square. Sigma yi, sigma xi square. So sigma yi, sigma xi square, sum, np sum. What do we need to sum? X we need to sum. This is sigma xi, np sum, y, sigma yi is also here. Oh, sorry, sigma xi square is required. Sum x square minus sigma yi minus xi square. So this is not, okay, sorry, yi minus xi square. Is correct? Yes. Now xi into xi yi. So np sum x1, which is xi yi. Okay, this is one thing. Now we need to divide it with, this is not complete, dividing it with n times xi, where n is the number of points, I from 1 to n. So n is equal to length of x or length of y, whatever, both are same. N, once again, np sum. On the denominator, we need to sum x minus sigma x the whole square, sum x the whole square. np dot sum x square. Okay, that's it. And similarly, we need to get y as well. Sorry, b as well. B is equal to n sigma, instead of yi, we need x here. Oh, sorry, n sigma, not this, n star sigma xi yi, minus sigma xi, sigma yi, sigma xi, sigma yi. Okay, the numerator is fine. Now n sigma xi, n sigma xi, that's correct. The denominator is exactly the same. So a and b are here. Now what is this a and what is this b? Print a, b. Is there any problem with the formula that we have? Let me just see. Or let me print Okay, let me just try to see all the values first of all, whether they are all correct. Print this. That's y is 114. That's correct. If I compare with the values available in the textbook. X 75. That's also correct. Sigma xy. Let me see. What is that? Oh, sorry. Print 1885. Correct. Xi square. 5625. No, xi square doesn't seem to be. NP sum. Oh. No, I have not taken xi square, but instead of that, I have taken sigma xi the whole square. That's a mistake. 1375. So I need to. Where is it? Sigma xi. The whole square is coming on the bottom. On the top, it should be sigma xi square. That's correct. Here it's sigma xi square only. So all the values are correct. 75, 114, 1885, 1375. 75. The number of points is x1, y1, x2, y2, etc. up to x and yn. Okay, I think the number of points given in the textbook is not correct. That's why I'm probably getting not exactly the correct number. The value used in the textbook is actually n equal to 4 is used, but here actually there are 5. I guess if I use 4, let me see if I'm getting the correct thing. Minus 2.88. That's also not correct. 0.7 and 12.3. So anyway, this seems to be. So let me just see the formula once again. So sigma yi, sigma xi square. Okay, sigma yi. I'm checking the formula once again. Sigma yi, sigma xi square minus sigma xi, sigma xi yi. That's fine. There is no n on the top. Bottom there is an n. Sigma xi minus sigma xi the whole square. Okay, let me just try once again to see if it's correct. Here also let me put a bracket. Okay, B is n into sigma xi yi. That's correct. Okay, n into is applicable only to this. So that's probably a mistake. N into is here. NP. Okay, then I should put a bracket here. N into sigma xi yi minus NP x sigma xi sigma yi. That's correct. On the denominator, n sigma xi minus sigma xi the whole square. Okay, let me just check. Minus 2 point, but still the n taken is not correct. Minus 2. If n is taken to be 4, the value given in the problem is 0.7 and 12.3, which we are not getting.
So after A star, there should be a bracket, I think.
Where?
In A, denominator of A, n star. After n star, is there any bracket? Because
Yeah.
n star it's n multiplied. This means n multiply only for sum of x, right?
N is multiplied only to sigma sum of x. That's correct. According to formula, that's correct.
Okay.
N should be multiplied only to sum of x, not to the whole
Oh,
thing.
okay.
That's correct. There is no, and not only that. Okay, only in the formula we are getting there because, but the thing is that they are taking n to be equal to 4. Sum of xi we are getting to be equal to 75. That's correct. Sum of yi we are getting to be 114. That's correct. Sum of xi square summed 1375 is correct. And xi y 1885, that's also correct. 1885, that's correct. So all these numbers are correct. The formula is also correct, but the final result seems to be somewhat different. A is getting us 0.7 and B is getting us 12.3, which is doesn't seem to be correct for us. So not only that, n is taken to be 4, but even after putting n equal to 4, we are not getting it. So there is something wrong. Okay, let us try to plot and plot the data and see if it's somehow matching. Okay, so plotting now from sorry import as plt plot. What is it here? A and B have been already found. Plot what? XY data we can plot. XY, and at the same time we can try to plot the F data also. X, and instead of Y we can plot AX plus B. Let's try to see how does this look. Oh, such a large distance. Okay, let me just try to see if I use 0.7 and 12.3 instead, if I'm getting the correct thing or not. 0.7 and be equal to, that is given in the textbook, 12.3. So use this. Oh, that's correct, but there is something wrong. Okay, but instead of that, okay, let me just try, instead of using the straight away given formula, maybe we are doing something wrong here. Instead of using the straight away formula, let me try to use the formula that sigma ya is equal to nb a sigma xi. Okay, let me just try to, without using this formula. I'm not getting it using this formula, but instead of that, solving sigma ya is equal to, but how do I do that? Equation equal to equation 1 equal to np dot sum. Okay, for that I need the symbolic Python from sympy import symbol. So instead of doing this, instead of straight away applying this formula, I am trying to use the relation connecting A and B given in the textbook. Okay, that's it. So A and B are defined to be symbols A and B. Later we will try to solve for A and B. So these are two symbols. Now equation 1 is a relation connecting AB and xi, sigma xi, sigma yi. The relation is that equation 1 is that sigma yi minus or nb plus a into xi. The formula is this: np nb, where n is already given here, nb plus a into some xi, which is this, minus np sum y. That's one formula. Next is 60. Okay. Next is equation 2. Equation 2 is that b into xi, b into some xi, b into some xi plus a into some xi square, sum of xi square, in b dot sum of x square minus sigma xi by a, x star y. So these two equations we solve for a and b. Okay, that's what essentially we want from sympy import solve. Now solutions equal to solve equation 1, equation 2, we try to see the equations first. Print equation 1, equation 2, so what are the equations? 75a plus 5b minus 114. Okay, is this correct? So 75a plus 5b minus 114, which means that equal to 114 we are trying to solve. That's correct. Next is 1375a plus 75b equal to 1885. That's also correct. So these two equations are correct. Now solve for a, b. Maybe we should solve, I think multiple equations are here. Maybe we should put it inside a bracket as a list. Solve for a and b. A and b, the expressions are here. Solve is already here. Okay, let us put it as let me just remove all these. Oh, sorry, that is not printed. I'm just trying to do something which, okay, that's completely nonsense. So what are the values of a and b? A we are getting to be 0.7 and b to be 12.3. Okay, there is something wrong with the formula, or I did not understand it correctly. So this is correct. This seems to be correct. A and b values are seeming to be correct. So a and b we are getting to be, okay, let me just update a with solutions a and b with solutions B. So solutions A and solutions B mean that. So here A is obtained as a dictionary. So to get this A out of this list, we need to use, this is solutions. Okay, this list is solutions. Solutions in bracket A we should use. In bracket we should use, yeah, this A, not this A. Oh, what's happening here? List indices must be integers, so slices not string. List indices must be integers, or is
The
A
it's a bit, resolutions B for
like this, straight away like this. A is equal to solutions A. So it's given as a dictionary. Okay, let us try to see once again. Print solutions. What is it here? Okay, let me just try to suppress this. Can't convert expression to, where is that happening? Okay, here, all these things I'll suppress. So A is given to be this, B is given to be this. So if I turn off dictionary, okay, let us turn off dictionary and see. Okay, previously we are getting it as a list. That's the problem, probably. Okay, 0 was also required. That's such a. So I think we needed to use solutions because it was coming to be something like this. Now let me just try to see. Here A itself is, I think we should use A value. Key error A. There is no. Okay, what is this now? Print solutions is what? What the result is? A is equal to this and B is equal to this. So if we do not use A at all, will it work? Okay, now it seems to be giving the correct thing. Okay, that's correct. Maybe in that case, we don't require, we can just take this to be this. Remove it. B equal to this. AB. AB seems to be correct. Solutions is not required. AB also not required. Matplotlib, fine. Show. Everything is fine. So now need, let us put the legend also. How did we put the legend there previously? Okay, this is how we should put the legend. X is the blue line and the straight line is in orange. Maybe if you want to see the straight line in, or the X curve in dot, say G dot, you can see the points are here. Maybe if we increase the number of points, maybe we will be getting something better. So this is how we should use, this is how we are using the least square line fit for a given data. Let me update the Google document with this. Start, update. Okay, that's the interpolation using least square. Now, so this data was quite straightforward. This data was actually okay. We have constructed our own data, but instead of that, we can create random data. We can create some random data and try to see how the this plotting is, this curve fitting is working. So for creating random data, we can use a numerical Python module called NP random. Something like this. Okay, let us start. I'm just copying the entire thing to a new program. Just to see once again, one more example using this and least square line. Or otherwise, the random. So how to generate random point itself? I'll just give. So corresponding to the same x values we can use probably. Random fit. Okay. So y values can be taken to be something random. NP random rand. Suppose we generate. So how many values are here? 5 values are here. Suppose we generate 5 values in y. So not 54, it should be actually 55. So if you print y, we are getting some values like 0.29, 0.89. Okay, if you use 30, what do we get? So all the values are between 0 and 1. And if you want to get random numbers between some particular range, suppose that you want to get random numbers between some range, say 0 or 10 to 20. Suppose that you want something like that. I think you need to specify some keywords, like you use keywords like low and high. Sorry, a random uniform. And size also you need to specify. Size equal to 30. So you are getting 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 30 values you will get using random uniform. Uniform in the sense that the random values are to some extent uniformly distributed. I don't exactly know what's meant by uniformly distributed. Some kind of uniformness is there. So you will get random values in this range. So you can try to plot, you can try to fit this random values also to see how effective our technique is. Let's try to see, for example, everything else exactly the same, trying to plot. The only thing is that random values are used here. Okay, the feedback link, just post it. Okay, I have posted the feedback link to YouTube also. Now, okay, what we are trying to do, trying to plot. So everything else remains exactly the same. The only difference is that size equal to. Okay, let us change. Let us push this here. Suppose we take instead of 5. Suppose we take 30 linearly spaced 30 data points. So size equal to n, exactly the same size we will be getting. Now everything else exactly the same. There is no difference. Now printing. 2 is not an integer. Where is that? Y equal to np random uniform size n. Is it here? The C. Print. That seems to be fine. Where is the problem then? Import symbols. Sum x square x star y np random. I think it's not an array. That's the problem. Okay, this is just a list np array. Let's convert this into. Okay, trying to print y once again. Yeah, y is anyway an array. What's the problem there? Where this 2 is coming into the picture. These things are not required anyway. Solutions. Undefined name solved. Did we suppress that previously? Oh, how did we do that? Equation is eqn 2. That's fine. What's happening after that? From sympy import solve. Is the problem here? Print solutions. Let's try to see once. eqn1, eqn2, n, a, n, p, symbol sum y. What's the problem with these equations? So equations are anyway fine. 450a, 30b. Is it because 450b, 78a minus something? Why it's creating the error here? From sympy import solve, solutions equal to solve, eqn2, eqn print solutions. Not an integer. What is not an integer? NP linear space 30. Okay, this is not required here probably. Okay, let me just use ran here. Maybe I will turn this off and see after that. Solutions A, B. So the error is here. eqn1, eqn2. B star, A and B are symbols. Symbols is already exported. Sum of x. A star np sum of x square minus np sum of, I think some compatibility issues is here. 2 is not an integer. Why 2? Why 2 is not an integer is given here. Value error. Is this 2 giving the error? 2, 2, 2. 2 is not an integer. Is it taken as a string or what? Sum x square. Okay, eqn A, eqn B type. Eqn A, eqn B, A, B, x is equal to np linear space. Okay, what is this x? So far this was working fine. Why suddenly it started giving the trouble? np is this. Is there a difference between this line as well as np linspace? np linspace in 525 5 is taken. 525 30 points are taken. X is given here. np array what is the difference essentially here? So y is taken to be np random. So what's the problem here? Print type of y, numpy nd array. That's an array. Now print type of x. Is there any compatibility issue? Both are arrays. There is no such problem at all. Importing symbols. So print a. What is a? A is just a. So b should be just b. Equation 1 and equation 2. So is the problem here? Equation 1 and equation 2, there should not be any such problem. Print eqn 1. So 450a 30b minus 12 point etc. That's fine. So is it large or anything like that? Equation 2. Okay, let us see if it is very large. So the second, where is the second equation? Equation 2. 7818 into a, 450 into b minus this. There is no problem even here. So import solve. Okay, is the problem here? Solutions is equal to solving equation 1 and 2 and dictionary is 2. The problem starts here, but why is it like that? The equation seems to be exactly, there is no problem at all. So, okay, I will try to check that anyway. The least square fit, and I will try to explain the polynomial fitting also. So the direct, so after least square line fitting, the next thing we should see is least square quadratic fit, which actually uses a quadratic polynomial. And we can even try to see least any order, any polynomial, any degree polynomial fit also can be tried. But what the theory says is that if the degree of the polynomial increases, the fitting is going to be not very useful, because it tries to capture all, it tries to go through all types of points, and the curve is not going to be that much useful. I have not completed this part. This I wanted to just show fitting the random points also, so that previously we were having a set of nice points. So seems to be some trouble. I could not actually locate what exactly the error is. Maybe we can try to solve that. We can try to go through this error message. I may have to just go through all these error messages and try to find out what exactly the error is. I will try to do that. I'll try to explain that tomorrow. And maybe with that, we will probably stop today's session with this problem leaving incomplete for today and trying to complete this tomorrow. And tomorrow we will complete this part and complete this curve fitting, and we'll try to solve, we try to find approximate solutions of not only polynomials but equations using bisection method and Newton-Raphson method. These two methods we will discuss tomorrow. And with this, I'm stopping today's session. Thank you very much for your patient listening. And if there is any clarification required, I can try to give that. Please proceed with your questions if there are any. Thank you.
No questions? So we are going to conclude this session. Thank you, Vishnu sir, for the nice presentation. And I also thank everyone, every participant. Okay, thank you all once again. So we can wind up the program. Good night.
Okay, as I told, I will try to find out a solution for this. I am unable to locate what exactly the error is. Okay, anyway, if you are also able to find out what exactly the error is, you can also try, because I will copy and paste the entire code, whatever I have done so far. And you can try in Colab. I don't know whether it's a problem with Spider or not. You can try in Colab also to find, if you can locate the solution, you can please give me a comment from your side. Okay. Okay, thank you very much.
Yes, sir.